And welcome to today's webinar on solar system to black holes, a retrospective of the new astrophysics by Professor Prajval Shastri. This webinar is the popular science lecture organized by Indian Women Scientists Association, Vashi, Navi, Mumbai, and it is supported by BRNS-DAE. This webinar is in association.
All are requested to mute.
All participants are requested to mute their mics.
Yes, everyone is requested to mute their mic, please, everyone. And this webinar is in association with Department of Physics, the Institute of Science, Dr. Homi, Bhabha State University, Fort Mumbai. So now, let us begin with our today's webinar. So to start with, I'll request our director, Dr. Jairam Khobragade sir, to kindly give a short introduction of our Institute of Science. So sir, you can start. Director sir.
Good morning to one and all. On behalf of the Institute of Science and Chairman of Organizing Committee, it's my privilege to welcome the distinguished guest, Professor Lalita Dhareshwar, President of Indian Women Scientists Association, Mumbai. Today's speaker, Professor Prajval Shastri, retired professor from Indian Institute of Astrophysics, Bangalore. Delegates and my dear students who have joined this webinar from different parts of the country. The webinar is on solar system to black holes, a retrospective of the new astrophysics. This webinar is jointly organized by Indian Women Scientists Association, Mumbai, and the Department of Physics Institute of Science. The Institute of Science, Mumbai, formerly known as Royal Institute of Science, established in 1920. This institute is managed by the Government of Maharashtra Higher and Technical Education Department, and now it is converted into Dr. Homi Bhabha State University, Mumbai. This institute is premier postgraduate center for teaching and research in science. It is the only center for postgraduate education in University of Mumbai until HBSU is established. The institute has been an alma mater to many industrialists and educationalists. Distinguished scientists Dr. Homi Bhabha, Dr. B.M. Udgaonkar, Dr. Menon, and Dr. Sri Ram Abhyankar are amongst the alumni of this institute. Dr. Kiran Karnik, ex-CEO, NASCOM, Padma Bhushan Madhav Gadgir, Madhav Chauhan, and several educationalists had been the faculty members of this institute and physics department specially. The Department of Physics offers courses and electives for the first and second year PG programs. The department has been successfully running a master's program in physics, that is MSc, with special emphasis on material science, solid state physics, solid state electronics, and condensed matter physics. We offer postgraduate programs as well as doctoral research program for highly motivated students looking to pursue a career in physics. We are now have DST FST supported department. Using the funds sanctioned by Department of Science and Technology, the postgraduate and research programs will further be strengthened by improvement of research facilities, also infrastructural facilities. The department presently has 4 core faculty members, 1 professor and 3 associate professors. Several distinguished people from industry and other reputed institutes and colleges are associated with this physics department as a visiting faculty members, giving quality input to education and training to the students. The faculty members are actively engaged in both teaching as well as research activities and have active national and international collaborations. Recently, we have MOU with TIFR. Faculty members have research projects from RGSTC, DST, BRNS, UGC, etc. Currently, thrust areas of research in the department, which can broadly include polymer nanocomposites, plasma processing of materials, nanomaterials, energy storage and electrochemical sensors, supercapacitors and fuel cells, magnetism and transport in quantum materials, computational soft matter research, solar thermal applications. The department has an endowment trust under which eminent scientists in the areas of applied physics are invited to deliver a series of lectures. Once again, I welcome you all to our institute, and I hope you will have very exciting and enriching academic sessions of the webinar. Thank you very much.
Okay, so now we have completed with the introduction of Dr. Devaki Ramanathan ma'am.
You have already.
I had like to.
Okay, you have introduced me. Okay.
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 Otherwise, I'll request again to Dr. Homi sir to introduce because of some sound obstruction might have happened. I request sir. So please.
Yeah, okay. It's my great privilege to introduce Dr. Devaki Ramanathan Madam. Dr. Devaki Ramanathan Madam is a physicist retired as a senior scientist from BRC, Mumbai. Her specialization was in ultra-high vacuum technology, surface science instrumentation like field emission, field ion microscopy, and PPV level mass spectroscopy like ICP-MS and GDMS. Beside a number of publications, her credit is in Northway to she had published papers on FIM in prestigious Nature journal in 1977, co-authored with two colleagues. After her retirement, she has been actively involved in NGO in Indian Women Scientists Association. She was president in Indian Women Scientists Association from 2015 to 17. Presently, she is a member, Board of Trustee of Indian Women Scientists Association and convener, Science Awareness and Subcommittees of Indian Women Scientists Association. Thank you, Madam.
Thank you. Did Dr. More get my slides of PPT from of IBSA? Otherwise, I'll manage without the PPT. It doesn't matter.
I received the slide.
You have not received?
Yeah.
Okay, doesn't matter. I'll give a very short description without the PPT. I think I can manage, and yeah, I think I can still instill some interest in all your students without PPTs. My voice is at least loud enough. So it gives me great pleasure. I don't know who welcomed me. Is it Dr. More?
Yes, madam.
Okay. Thank you, Dr. More. And it gives me a great pleasure to welcome all of you for today's lecture and to give a very brief introduction to our NGO, the Indian Women Scientists Association, which is collaborating in today's talk under the banner of the BRNS support. Our NGO is located at Vashi, Navi, Mumbai. We have a big plot of about 5,000 square feet area in which we have a number of a big sprawling building. I'm sorry, I cannot show you in the PPT for that. But this organization, the Indian Women Scientists Association, which is acronymed as IBSA, was started in 1973 by 12 founder members, all reputed women scientists, with the objective of taking science to the masses, developing a scientific temper in the society, and to empower women at large. Today, this association has grown to a strength of almost 2,500 members with 11 branches across the country carrying out these mandates. Essentially, our programs can be separated into two arms, the social and the scientific pursuits. On the social front, you have a working women's hostel, which can house at least 160 people. And then we have an activity block, which includes a daycare center, a nursery school, a nursery teachers training program, a computer center, a library cum reading room, a health center, a laboratory, and a learning garden activity with flora and fauna from all regions, which are all housed in this campus. We have successfully run a one-year diploma course for early childhood care and education. We have been running this for the last 25 years. And now we have added short-term training for inclusive education and shadow teaching. Now, these constitute the community welfare activities. Under the science education initiatives, there are programs run throughout the year for school students, which constitute laboratory practices, lectures, camps, exhibitions, etc. For college students and teachers, we conduct workshops, seminars, conferences, refresher courses, lectures like this, and open-air laboratory learning at our own garden and in-house green initiatives. I invite all of you to visit our campus sometime, maybe after the COVID is gone, to see how the compound is always brimming and buzzing with activities carried out by our dedicated volunteers. The pandemic brought a big change. We have to adapt to the new normal, and like all other educational institutions, we did. And our webinars have become handy to meet and carry on. Now we regularly conduct, beside our meetings, 2 series of webinars. I would like to mention them because they are of great interest to us. One is called the Member Enrichment Program. These are Wednesday webinars open to school students and our own members to learn and improve our knowledge on all aspects of gardening, plants, flora and fauna, etc. The second is the Science and Our Life series webinar. This is open to the society at large, not only to our members, and it covers all scientific and technological pursuits that have helped us to understand science around us, science in our everyday life, science within us, science of all issues governing, limiting, and developing our own existence. This is a once-a-month webinar, and eminent scientists like Padma Shri Professor Rohini Godbole, Tessie Thomas, they have all taken this platform to address us. Next week, we are celebrating Science Day, which is our annual event, by conducting online contests for school children, where they will showcase technical models or PPTs on a scientist and his invention, or a computer app on the scientist. There are almost 50 entries that we have received for this competition. Now, today's talk is sponsored by the BRNS of the Department of Atomic Energy, who have been supporting us generously to conduct these series in different colleges of Mumbai and Navi Mumbai. We bring in experts, preferably women, and the objective is to inspire students, especially girl students, to take up science for higher studies by providing role models. These popular lectures, we have had 23 during the pandemic as online series at headquarters and at branches, and they have been received very well with very encouraging outreach figures. I'm sure you would be motivated and looking forward to hearing our today's eminent lecturer and her exotic topic. Over to you, Dr. More. Thank you very much.
Thank you, ma'am. Now, I'd like to introduce today's speaker, Dr. Prajval Shastri, ma'am. Professor Prajval Shastri is an astrophysicist of over 35 years. She got her PhD from the Tata Institute of Fundamental Research and held postdoctoral research positions in the University of Smithsonian for astrophysics before specialized in center of this operating infrared optic violet and to the distant galaxy and been right fellow at senior and for and a distinction the extremely passionate science which besides the cultivation of scientific aspects of of all ages national campaign I joined the funding to train trainers in awareness building and reach thousands of students and across the country. We ran a wave-based Copper Moon Rising campaign across South Asia during the lunar eclipse of 2018 and distant sun campaign leading up to amber eclipse in December 2019. She is also deeply concerned about the gender disparity in the sciences. In addition to her research publications, her published work includes popular articles on astrophysics and on the subject of science and society. So when such a eminent personality is with us, so why not to have a knowledge treat from Dr. Prajval Shastri ma'am. So I'll request Dr. Prajval Shastri ma'am to kindly move ahead with the presentation. Please, ma'am.
Can you hear me now? Hello, can you hear me?
Yes, ma'am. Yes, yes, ma'am. You
Okay.
can start sharing the PPT.
Okay, I'll do that. So you should be seeing my first slide now.
Yes, madam.
Yes, yes.
Okay. So thank you very much, everyone, for this opportunity. I thank particularly the Indian Women Scientists Association and the Institute of Science for having me chat with you today. Many of my mentors and teachers have been alumni or are alumni of the Institute of Science, so especially my mentors and teachers in physics. So this is a particular privilege for me to be talking here. So astrophysicists use the laws of physics that we infer here on Earth in order to understand what we see in the cosmos. And for many decades now, astrophysicists use cutting-edge technology, and that thereby many of the universe's mysteries are unlocked, but also many new mysteries keep bubbling up. So today I will give you a few glimpses of some of the recent exciting developments that we've had. This would be a typical night sky if most of us did not live in places with extreme light pollution. But there are still places on the planet, for example, in Ladakh, where this picture was taken, where the beautiful sky is still visible. In fact, a side point here is that, it is our responsibility, each of us, to try and preserve this human heritage, both in our individual spheres, by adopting the correct kind of scientific kind of lighting to only light up our lives on the ground and not waste light out into the sky, and also to join collective advocacy to stop the kind of assault that is happening on our sky and the light pollution and so on. So to come back to the sky, this is a typical view that one would have seen, and from a big city like mine or yours, we would see only the brightest of these and not the thousands of other pinpoints of light that we see. But also what we're seeing here is what the human eye can see, which is visible light. The electromagnetic spectrum spans radio frequencies right up to X-ray and gamma ray frequencies, as you all know very well. And astrophysical objects emit at all of these frequencies. And so when we look at them in frequencies beyond the visible light, then new physics emerges. And this has been the big advance in the last century. So the atmosphere is not transparent to all frequencies, and visible light and radio light do reach the ground, and some amount of infrared light also reach the ground. I had a question. So are you able to see my pointer? So right now I'm pointing at the...
Yes, madam.
Okay. Right. So the atmosphere does allow visible light and radio light and some amount of infrared light when you go very high to high altitudes to reach the Earth. But to access, say, gamma rays or long infrared frequencies, we have to go above the Earth's atmosphere out into space. So these are some examples of the kind of telescopes we use. So here is the Venubappu telescope, which the Indian Institute of Astrophysics operates, and it's in Tamil Nadu, operating at visible frequencies. Here is the Hubble Space Telescope, also visible frequencies, but it has outside the atmosphere, and so can get very sharp images. This is the Chandra X-ray Observatory. This is a Spitzer infrared telescope. This is AstroSat. It's an Indian satellite which has ultraviolet and X-ray telescopes. And this here is the giant meter wave radio telescope, which is outside of Pune. One digression before I proceed. So when I say that we look at frequencies which is outside the human eye's range, how do we actually then render the data that we get from the cosmos, especially the images that we get? How do we render them? Because we can't see an infrared image, we can't see a radio image. So what astrophysicists use, I mean, there are many methods to render these data, because the data come from the telescope onto a sensor and onto a computer. So we have a bunch of numbers which represent a radio image or an infrared image or something. And in order to, and also visible, the visible images also go into the computer and become a bunch of numbers. So how do we render that? So this is what one would call a true color picture, in this case of a cat. Now, if I took a picture of that cat in infrared, as you would expect less infrared emission from the nose of the cat, which is very cold, and more infrared emission from the ears of the cat, which are warmer, and something in between from the body. Now, that is what is represented here, but it is a false color picture, meaning to say that the colors here are not real colors, obviously, because this is an infrared picture. So obviously there is no green or blue or orange light, but it's a false color picture where each color represents the intensity of the light received, whatever frequency it may be in. And it's not a color. So that's why we call them false color pictures. And this is one of the best ways to render images, especially, and also spectra of things that we see in the sky, especially when we measure them outside of the visible range. So this is another rendering. It is the same kind of picture, an infrared picture of the cat, but here the renderer has used a different set of colors, and so the colors are arbitrary. So this kind of image doesn't make sense unless it comes along with a key to tell you which color represents which intensity. And so the same data, for example, is represented by somebody else with a different set of colors and therefore a different key, but the data are the same. So this point is something to remember. And these two galaxies are, again, real images of two galaxies in the cosmos. These are what are called true color images, meaning to say that the detector sends red, green, and blue, and they are mixed in such a way to render them in a way that the human eye would have seen. The human eye can't see such sharp images, but the color rendering is to mimic what the human eye would see. And these are images, they're two identical images of the planet Uranus. On the left is a true color picture, and on the right is a false color picture, where the colors represent intensity rather than the color itself. Okay, so that was a digression to remember. And so when we look at the cosmos and measure the light at different frequencies, new physics emerges. So this is a very famous galaxy called the Sombrero Galaxy, and you can see the distribution of stars, and you can see this dark band in between. This is a picture in visible light. But if you look at it at other frequencies, so here on top in blue, this is a false color picture of the X-ray image of this galaxy, and you see that it looks very, very different. This is the visible light image, which I showed earlier, but rendered as a false color picture, and that dark band you see here. And here you see the X-ray image, which is very different because we see X-ray emission from stars which are distributed all over the galaxy. And it turns out that this dark band is due to dust that is spread within the galaxy in a disk-like geometry, and that emits in infrared. And so if you take a picture of this galaxy in the infrared, this is what it looks like. So here you can see what looks like a dark band here is actually lit up, and you see the disk of dust very clearly. And you also see emission from the stars, especially the older stars, because they tend to emit in infrared. So that is just to illustrate to you the multicolor nature of things that we see in the cosmos and how it can reveal new physics. So all of you know that the speed of light is 300,000 kilometers per second. And one thing about the cosmos and studying the cosmos is that, for example, it takes light 1.3 seconds to reach us from the moon and 8 minutes to reach us from the sun. So we say that the moon is 1.3 light seconds away from Earth and the sun is 8 light minutes away from Earth, where these things are units of distance rather than time. And the point is that we on Earth are always out of date. So what we see on the moon happened a second ago. We can never see something on the moon which happened like now. And what we see is happening on the sun happened at least 8 minutes ago, because we can never see something earlier than that. That's just because of the speed of light. Okay, a very powerful tool that astrophysicists have is a tool of spectroscopy. Now, all of you are very familiar with spectroscopy. You know that things which are hot emit a continuum, as you can see here, which if you put through a prism will come out like a rainbow. If you have something like a cloud of gas in between the source and your detector, then you will see absorption lines in the spectrum, just like we see the Fraunhofer lines in the sun. And if the cloud of gas itself is emitting, then you will see an emission line spectrum. And all of you know that these emission lines or the absorption lines, will reflect the composition and what elements are present there. So for example, carbon has this kind of spectrum, oxygen, nitrogen, iron, and so on, which you're very familiar with. And so if you have a cloud of gas which has a mix of all of these, the spectra will be like an overlap of all of these. However, there are two reasons why astrophysicists use these things to go beyond just the composition. So composition, of course, is one important inference one can make from spectra. But there is the issue of Doppler shift. So if you have a source which is moving away from you, that the frequencies that source emitted will be so-called redshifted, meaning the frequencies will become shorter, lower. And if the object is moving towards us, the frequencies will become higher. And so if you have lines, like atomic lines, they will shift and they will be seen at frequencies which are either lower or higher than the laboratory measured value, depending on whether the source is coming towards us or away from us. This may be a star, it may be a hot cloud of gas, it may be a galaxy, whatever. And so, therefore, the spectra give us a handle on the movement of these objects in our line of sight, which is a very, very powerful tool for us. The second reason why spectroscopy is important, of course, this is the third reason actually. The first reason is composition, the second reason is measurement of motion, and the third reason is that the universe is expanding, and therefore space-time is stretching. And therefore things which are far away, when they emit light, that light is stretched before it reaches us, and therefore the frequency of lines becomes lower because of the expansion of the universe. And this is something we call the cosmological redshift. And apart from the question of why the universe is expanding and so on and so forth, which I won't go into, it is a powerful tool for people like me who study galaxies and what is inside these galaxies, because the further away something is, the larger is its cosmological redshift, and therefore by measuring the redshift, I can measure how far something is from us. So these are the three reasons why spectroscopy is a very powerful tool. Another small digression is that in astrophysics, you probably know this already, but we find the units of mass as kilograms or power as watts quite cumbersome because the numbers are very large. So we tend to use the mass of the sun as a unit for mass. So this is the symbol for it, and the unit of luminosity as the luminosity of the sun. So we say something is 5 solar masses or 3 solar luminosities. Now, the brightest object in the sky, the night sky, is the moon, of course, as all of you know, and have probably seen many times. The next brightest object is the planet Venus. So here is a picture of the sky taken from Ladakh, and this very bright thing which has saturated the detector is the moon, and the next bright thing is Venus, and here's Jupiter. So Venus, of course, being the next brightest thing in the sky, has been observed by many civilizations over the history of time. It has many names. Shukra, Zohra, Pasang in Ladakhi, and Venus. It is also associated with many myths. For example, in Vedic mythology, it is associated with Shukracharya. In Mesopotamian mythology, it is the goddess Ishtar of war, love and war, and so forth. It also appears on many flags, national flags, and incidentally, the flag from Turkey is the one which correctly astrophysically depicts it, because the planet Venus is outside of the lunar disk. It obviously cannot be inside it because Venus is further away from the moon. So one of the first people who studied Venus in detail is, of course, Galileo Galilei, and this is his sketch. And he discovered the phases of Venus. In other words, the disk of Venus is a planet, after all, shows phases just like the moon does. So there's a crescent Venus, a gibbous Venus, a half Venus, a full Venus, and so on. And he realized that the only way that can happen is if Venus is in an orbit around the sun, which is smaller than the orbit of the Earth. So only Mercury and Venus, which have orbits smaller than the orbit of the Earth, can show you phases, right? This is just a montage of the phases of Venus, which was created by this amateur astronomer Prabhu Kutti, and put it all together. So the phases of Venus, yes. So the phases of Venus tell us very clearly that Venus is in an orbit smaller than the orbit of the Earth. Now, in size, Venus is roughly the size of the Earth, and also its orbital period is roughly the same. So for a long time, it was sort of thought of as a twin planet of Earth. But May I request people to mute their mics?
विकी के पास जाओ उधर ही आएगा।
चलो एक आप भी चलो मैं उसको 50 बार बोला मैंने विकी को
काम उसका ही है।
Yes, I request mute everyone your mic, please.
चलो ये 1 साल के अंदर मेरा टाइम है 1 साल
Thanks. So Venus was sort of thought of as a twin of the Earth, but further investigation revealed that the surface temperatures of Venus are extremely high, something like 460 Celsius, and the pressure on the surface of Venus is also, the atmospheric pressure is also extremely high, more than 100 times what it is on Earth. So then people sort of concluded that it was a very hostile sort of atmosphere. So when people imagined life outside the Earth, they thought more about Mars, and there's all this science fiction lore about Martians and so on. But in 1967, Carl Sagan proposed the idea that although the surface of Venus is hostile, as you rise in the atmosphere of Venus, then you get to lower and lower temperatures. So even though on the surface of Venus it's 460 Celsius, as you rise up it's going to be cooler, and so at about 50 kilometers altitude the temperature would be like room temperature. So that part of the atmosphere of Venus in theory could harbor some sort of living organisms like those found on Earth. So this was an idea that Carl Sagan propounded in the late 60s. And recently, a scientist named Jane Greaves and her team investigated this question. So we know Venus has an atmosphere, as is seen in this picture here. She looked for signatures of microorganisms using a telescope in Hawaii called the James Clerk Maxwell telescope. So she used millimeter frequencies in order to look for signatures. And what she found was absorption lines due to a molecule called phosphine. So phosphine is P and H3, and it's not an easy molecule that occurs in nature. It is known to occur in Jupiter and Saturn and that is explained because in the cores of Jupiter and Saturn there are very extreme conditions, high temperature and pressure, and then they're gaseous planets. So this phosphine gets created in their cores and then floats up. But otherwise, it's extremely difficult to make phosphine. On the other hand, on Earth, it is known that some microorganisms make phosphine. And so therefore, phosphine is seen as a sort of a biosignature, shall we say. And what Jane Greaves found was that she found an absorption line signature for phosphine. And these are her data. So the yellow curve represents the absorption spectrum, and the red curve represents a simulation to determine quantitatively what is the amount of phosphine, or the relative amount of phosphine, let's say. So she found this with the James Clerk Maxwell telescope. She was not satisfied with it, so her team went ahead and re-observed Venus with this telescope, which is the Atacama Long Millimeter Wavelength Array. And so it's a much more powerful telescope at 5,000 meters altitude in the deserts of Chile, and she confirmed her result. So she confirmed her result 2 years later, and so that means that this phosphine is long-lasting. At least it lasts at least a few years. This is the Atacama large millimeter array that she used for her second observation. And her team also investigated whether this phosphine could have been produced by so-called abiotic processes. So could the solar wind have caused it? Could volcanoes have caused it? Could lightning on Venus have caused it? We know there's lightning on Venus. Or could meteorites have brought the phosphine from outside into the atmosphere of Venus? They investigated all these possibilities and they came up with a negative answer. And therefore, they tentatively concluded that this phosphine could be a signature of life. They don't say there is life there. They say that it could be a signature of life and therefore is worth further investigation. So this was one of the exciting results that came out last night. Okay, so this is a picture of our solar system that we commonly find in textbooks. And even Galileo had discovered that Jupiter, for example, has at least 4 moons. This is his sketchbook and his illustration of these 4 moons, and these are more modern images of these moons. But if you think about the scale, it's a very difficult thing to have all these objects to scale. For example, here the sizes of these objects are to scale, but the distances between them are not to scale. It's very, very hard. It's a very nice exercise for you to do, especially when you're, let's say, teaching your maybe younger siblings or friends who are in high school about these things. It's a very nice exercise to do, to try and do everything to scale and see where that gets you. So I'm just trying to give you a sense of what that scale is. So this is our home, the Earth, and this is the nearest object to us, the Moon. And this is a diagram, again, where things are to scale. So you can see that Jupiter is pretty large. The Sun is, of course, enormous, and Earth is only this much. But yet this diagram is not to scale in terms of distances. So this is an example that illustrates that distance. So here is a photograph taken in 1977 by a spacecraft called Voyager. It had to go 11 million kilometers away to get the Earth and the Moon in the same photographic frame. So that's what you see here. This is the Earth and this is the Moon. And this is a picture taken by Voyager, which was at the time 11 million kilometers away. This is another picture taken by the Mars Reconnaissance Orbiter, flown by NASA. So this orbiter left Earth and went towards Mars, and then pointed its camera in the direction of the Earth. And Jupiter, very, very far away, was also in roughly the same direction. So they were able to get both Jupiter and the Earth on the same frame. So that is what is shown here. So this little dot here is Jupiter, and this even littler dot here is the Earth. So they are both in the same photographic frame. So you can see the sense of scale. And now if I zoom in this photograph, I zoom in to just Jupiter, you can even see the planets of Jupiter here and here. And if I zoom in to the part with the Earth, you can see the Earth and our Moon. So all of these objects are seen in the same frame, but it had to be taken from this satellite which went really far away. So just to illustrate that, this is like an imaginary trip into and out of our solar system from the Earth. So it's all empty space, as you can see here. We're passing Jupiter, Saturn, Mars, and so on. But most of it is empty space. And here we've passed the Sun, and then out of the solar system to see the nearest star. And you can see that even in between the stars, it's all mostly empty space. Now, these stars, all of them, therefore, are extremely far away. And although they look very crowded in some places, that's just because we are so far away from them. And in reality, the distances between them are of the order of light years. Now, all of these stars, I mean, all of these pinpoints of light, people have wondered about them. And you all know, and I've also said, that some of them are planets within our solar system. But others are all stars. They're all stars in our Milky Way. And it was a priest and scholar and scientist and philosopher called Giordano Bruno, who very early said that stars are other suns with their own planets. He got into a lot of trouble because of his views. And in fact, today is a day to celebrate. Today was the day that he died. He died because he was burnt at the stake. And he was burnt because people did not like the views that he espoused, and he refused to recant his views and apologize for them. So they finally burnt him at the stake because the mainstream knowledge at the time could not accept that many of the things that he said. But he was one of the first people to imagine that stars may have their own planets. And in that sense, today is a day to celebrate Giordano Bruno. So the nearest star to Earth is in the constellation Centaurus, and some of you who are amateur astronomers may have routinely watched this. And so there's this bright star called Alpha Centauri in it, and near that bright star is another star which is inside the circle with respect to the bright star, but is not visible to the naked eye, and that is a star which is known as Proxima Centauri, and it is the one which is nearest to Earth. Now it turns out that Proxima Centauri has a planet. It is the size, almost close to the size of Earth. And so Giordano Bruno's prediction, in a sense, has come correct. And Proxima Centauri's planet is not the only one. By now, we know of the existence of over 4,000 planets around other stars in our Milky Way. So how do we know that there are these planets around? We can't see the planets per se because they're too faint. As we know, planets don't have their own light, so they're not shining pinpoints. The stars are pinpoints of light, but not the planet. Then how do we see them? So there are two methods. One method is this, that you expect that the stars are going around, the planets are going around the star. We see the stars as a pinpoint of light. So we can measure how much light comes from it. Now you can imagine that when the star comes in front, when the planet comes in front of the star, that little bit of the star will be obscured by the planet. And so there will be a slight dip in the amount of light that is coming from the star. So by measuring that, you're able to say that this star has a planet. Of course, it's not enough for there to be just one dip. It has to be a periodic thing. The dip has to be periodic and repeated. So when all those conditions are met, we can conclude that this planet has a star. So this is one method. And this animation shows you not what we actually see, but what is actually happening. Because we can't see the star like this. We just see a pinpoint. And we can't see the planet either. But what we do see is this measurement. The amount of light which is steady from a star. And then when the planet comes in front of it, because of the planet's shadow, there is a slight dip in the amount of light that comes. So this is one method. The second method is spectroscopic. So a planet orbiting around a star will, what that means is that both these objects are orbiting around their barycenter, as you would have studied in your curricula. And so there is a slight wobble that the planet induces on its parent star. And we can see the star, and we can do spectroscopy on the star, and we can measure the spectral lines on it. And these spectral lines will do a Doppler redshift, blue shift, redshift, blue shift in a repeated periodic way if there is a planet, a sizable planet, close enough to it. I mean, the closer it is, the better detectable it is. So there are many such planetary systems now known. This is a really nice one, which where 7 planets have been measured around this, have been detected around the star. Okay, so back to the night sky. In the night sky, some of you would have observed the so-called constellations, like this is the Taurus constellation, this is the Orion constellation, but this here, and so you probably know that constellations are just patterns of stars which happen to be in those positions as seen by us, and they are not necessarily physically related. But this, which is the Pleiades, these stars are physically related. They were all born from the same gas cloud around the same time, and therefore they are all roughly the same ages. Now, what happens to these stars? So when they are born, they collapse and trigger nuclear fusion, and therefore they shine, and we see them as stars. Now, when the nuclear fuel is exhausted, if the star is heavy enough, The nuclear fuel is exhausted, so the hydrostatic equilibrium between gravity and the pressure generated by the nuclear fusion no longer is in equilibrium, and so the star collapses due to its own self-gravity. And if it is massive enough, it will become a black hole. So what is a black hole? Black holes are chunks of space-time from which even light cannot escape. So let us look at the idea of black holes in a sort of an intuitive way using this term escape. So as you all know, the escape velocity from a heavy or a massive object like the Earth, for example, is given by this formula, where m is its mass, v is the escape speed, and r is the distance from where you are launching something to the center of gravity. Now, we know that the escape velocity at the surface of the Earth is about 11 kilometers a second. For the moon, it's about 2 kilometers per second, because, of course, for obvious reasons. Now, what happens if you squeeze the mass of the Earth to a smaller size? So all of the mass of the Earth, you squeeze it. The escape velocity obviously increases because you've kept the mass the same and you've reduced the distance between the surface and the center. So now, suppose you squeeze it so much that the escape velocity becomes the velocity of light. Then what happens? You get a relationship between the size and the mass. And if the escape velocity is the velocity of light, it means that even light cannot escape from this thing. So it turns out that you would have to squeeze the Earth, all of the mass of the Earth, into a marble size in order to make it such that the escape velocity is the velocity of light. In other words, in order to make the Earth into a black hole. Now, those are impossible densities, as we all know. And this idea that something really heavy, if heavy enough, could be something that would not even allow light to escape from it and therefore would appear dark, is an idea that was documented very early. So these are two examples, John Mitchell in 1783 and Pierre-Simon Laplace in 1796. And they realized that it cannot be things that are Earth-sized or small-sized. So they imagined stars in the cosmos, really, really large and heavy stars that might collapse gravitationally in order to form objects whose escape velocity is the velocity of light. They didn't use the term black hole. But of course, they were very difficult to find, because how do you find a dark star, right? You would never see it because light would not escape from it, so it would be dark. Now, in 1915, Einstein, as you know, proposed his general theory of relativity, where it was a completely different way of looking at gravity. So what I told you so far was the classic Newtonian way of looking at gravity and everything else. Einstein came up with a new way of looking at gravity, which said that all masses, my mass, your mass, my laptop's mass, whatever, all masses curve space-time. And so the movement that we see, that we attribute to gravity, is because masses curve space-time and things move along this curved space-time. So that is why if you have the Earth, it would create sort of a, you can think of it as like a depression in this fabric of space-time, and so objects would go towards it. Other test particles would go towards it. And John Wheeler worded this very beautifully by saying, mass tells space-time how to curve, and space-time tells mass how to move. So this was an entirely new way of looking at gravity. And within a few months of this, Carl Schwarzschild found a solution to Einstein's equations for gravity. And this solution was identical to the formula for a black hole that I showed you earlier. So just looking at the escape velocity and deriving a relationship between the size and the mass. So then had Carl Schwarzschild found a black hole. So there was a lot of suspicion about this result. And it was not paid much attention. And anyway, the word black hole was not in usage at the time. However, Einstein's theory, since it said that mass curves space-time, it meant that light would also bend in the vicinity of a mass. And this was very fabulously demonstrated by Eddington during the 1919 solar eclipse. You probably are very familiar with this experiment, and therefore that was very strong support for Einstein's general theory of relativity. And of course, we know that this is now part of our daily experience because GPS satellites have to take into account the curvature of the Earth when in order for the GPS system to work. But at that time, despite the precession of the perihelion of Mercury, and despite Eddington confirming the bending of light, there was still a lot of question about Carl Schwarzschild's solution. People didn't like it, and also one of the reasons they didn't like it was because of this notion that it was a singularity. And singularities are not comfortable things. Meanwhile, or rather not meanwhile, but a few years later, Chandrasekhar discovered that when a star exhausts all its nuclear fuel, it will start to collapse, but it will not. If it is about a solar mass in mass, then it will not collapse completely because the electron degeneracy pressure will be sufficient to hold it up against, perhaps due to gravity. However, if that star is much heavier, then the degeneracy pressure would not be sufficient to hold up the star. And he made this statement, and one is left with speculating on other possibilities, although he didn't really spell out things about black holes. A few years later, Oppenheimer of the atomic bomb fame investigated it in detail, and they concluded that indeed there would be a Schwarzschild singularity when massive stars collapse. They correctly interpreted that there would be a surface. The Schwarzschild solution represented a spherical surface, which was in some sense a horizon. And they said it's an information horizon, that the star at collapse will close itself off from any communication with a distant observer, and distant observers, that is people who are outside the sphere, will only sense the gravitation, and they will not be able to get any other information from within. Now, this was still in the regime of mathematics and mathematical constructs, and they were not seen as real physical objects. Even Einstein did not quite accept that these could be real physical objects. But then, in the early 60s, a very strange object was discovered in the cosmos. It was called 3C273, and it's the object here in the center of this picture. And what you see is all a bunch of pinpoints of light, and this looks like any other pinpoint of light, nothing unusual about it. But the spectrum was unusual because most stars, I mean, people thought of most of these pinpoints as stars, and they show absorption spectra, like the sun shows the Fraunhofer lines. But this object showed emission lines. And then I told you earlier that the universe expands and so space-time stretches, and therefore the emission lines which are emitted by objects are cosmologically shifted to lower frequencies. Now, when the spectrum of this object was got, it was strange because nobody could recognize the emission line. They didn't match anything of the atomic emission lines that were known on Earth. Then it was realized that the reason people could not recognize them is because they are all shifted by about 16%. So then if you attribute that shift to a cosmological redshift, then you get a distance, and the distance of this object turned out to be huge. And therefore, the fact that we see it at all means that it is a very, 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 very luminous object. So it was plainly luminous. There was no way such luminosity could be produced from nuclear fusion in stars, from collections of stars, from stars all exploding at the same time. Nothing. In fact, George Gamow wrote this poem, Twinkle, Twinkle, Crazy Star, biggest puzzle from afar. How unlike the other ones, brighter than a billion suns, twinkle, twinkle, crazy star, how I wonder what you are. So the amount of power from this object was equal to the sum total of all the luminosity of all stars in a galaxy, whether it's a Milky Way or Andromeda Galaxy or any other galaxy. So this was very, very difficult to explain. And there was one more problem. As if this problem was not enough, there was another problem. And that problem is that this light came from a very, very small volume. So how did they know that? You can't get the size of it by just looking at it, because looking at it just tells you it's a pinpoint of light. But there is something we call the light travel time argument. It's a very, very simple but very powerful argument, and I'll just explain that to you. So if you're looking at a pinpoint of light in the cosmos, okay, which is represented by this gray circle on the left, and let us say it instantaneously brightens. If it instantaneously brightens, and if you're sitting right at it, you would see this instantaneous brightening. But we are here on Earth trying to look at this thing from a telescope, right? So then what happens is, this thing instantaneously brightens, but the photons, so in this plot, time is running along the horizontal axis. So as you go from left to right, time is increasing. So the photons from the front side of this object would reach us first, and photons from the back side would reach us last, and photons from in between would reach us in between, right? That is obvious. So if this thing instantaneously brightened, we wouldn't see it here on Earth as instantaneously brightening. We would see it as gradually increasing and reaching the maximum level. Now, over how much time would we see that gradually? If this is instantaneous, we would see it over a time that light takes to travel this distance. In other words, that light takes to travel the size of the object. So therefore, if we turn that argument around and say that we saw a change in the brightness of a pinpoint of light over a few weeks, then the size of that object cannot be larger than a few light weeks. So if we see something brighten over a minute, the size of the object cannot be larger than a light minute. So we call this a light travel time argument. It's a very powerful argument because it's very easy to measure variations in pinpoints of light, and it tells us about the source. So this very strange object, it had a name 3C273 for reasons that are not very important. It was not only enormously luminous, but it was very small. And this was extremely difficult to explain. So the only way to explain it was to invoke the objects that Oppenheimer and Schneider talked about in the late 30s. So near this horizon that Oppenheimer and Schneider talked about, there is a very, very strong gravitational field, and that field can be harnessed if stuff that comes near it goes around and plunges into this object. Then such stuff would be accelerated to very high temperatures, it would shine, and we would see it from very large distances. So these ideas were put forth by Salpeter in 1964, and Zeldovich and Novikov also at the same time. And so these objects were really needed. So even though, but the question still remained. So people said, yes, these strange objects must be black holes around which matter is swirling, which is what enables them to be very powerful even from a very small volume. But the question still remained, could these objects really be real, or was it an artifact? And would the matter that sort of collapses just eventually come out? Or could quantum physical effects prevent the collapse maybe? And it was Roger Penrose who came up with the answer to these questions. And he showed that without any constraining assumptions, but applying very rigorous topological methodology that he came up with, and also beautiful geometric intuition, he came up with this idea that it was inevitable that masses like that collapse into a singularity, but shielded by this event horizon around it, which is given by the classic formula for black holes, which is the relationship between the size and the mass. So I just here put up the beautiful figure that he drew in his original paper, where he, this is what is called a space-time figure. So time is going along the vertical axis, and he has suppressed one of the spatial dimensions. So you have only two spatial dimensions, and he has illustrated how mass collapses into this horizon, and it's a horizon of no return. So from inside the horizon, you can't get any information out. Once you cross the horizon, all directions lead into the future, into the end of time, so to speak. So he did not get rid of the singularity, but the advantage was that the singularity was shielded by this event horizon. And so we could study these objects without worrying too much about what happened inside that event horizon. So we do now know that there are about 66 at least black holes scattered throughout our Milky Way, and estimates are there are about 10 million of them scattered throughout the Milky Way. And this is just for your information that there's a catalog called Black Cat, which catalogs such black holes as they are discovered. So the other big discovery to confirm that black holes are real came in the form of the gravitational wave detection, which I'm sure you all heard about. So I won't spend too much time on it. This was the LIGO observatory that discovered two black holes coalescing in space because of the ripples in the space-time that they created. And they measured those ripples using a laser interferometer, which is shown up here. This is an artist's view of what must have happened. It's not a real picture. These are the real data, which illustrate the gravitational waves that they detected. And this discovery won the Nobel Prize. And I would strongly recommend that you listen to Gabriela Gonzalez's brief talk at the discovery announcement at the National Science Foundation, which is really a evocative and very clear description of the result. So now let's turn, I think I had a break in my internet. Did you miss anything? Hello?
No.
You didn't miss anything? Okay. Okay, so let us turn now to the Milky Way. This is a picture of the Milky Way taken from Leh. And of course, those of us who live in big cities, we can't see this view anymore. I could see it when I was a child, even though I grew up in a small city. But we can't see this anymore, and we have to go to these faraway places to see it. The reason is this. This is a picture of the Earth taken from the sky, and it shows you clearly all the lighting that modern civilization has started to use. And it also shows you that a lot of this light is waste and polluting. It's going upwards into the sky rather than lighting the ground where we actually need it. Anyway, that is a different issue. Now, the Milky Way looks like this band of light across our sky. And Galileo Galilei, again, was one of the first to turn his telescope to the Milky Way and show us that actually these white patches of light are because there are zillions of stars there. So the white patches are not some hot gas cloud or something, but they're just billions of stars. So Galileo Galilei had many discoveries to contribute, but I think the two most important contributions he made was, one, that he believed that science is for everyone. So he made it a point to take his telescope to the marketplace and show his discoveries to the public that would gather there. And also he wrote his texts in Italian rather than in Latin, so that a larger cross-section of people could access his discoveries. So this was a very important step to sort of stop making science out into this extremely difficult thing that only a few people can understand, but into something that everybody can understand and enjoy. And the other thing is that Galileo Galilei was the founder really of the scientific method. And so you have probably heard, it was the common knowledge at the time that heavier objects would reach, when dropped, would reach the ground faster. He questioned that, he got the answer through experiment. So this business that opinions must be based on the results of experiment and observation, rather than just believing what tradition might tell you, was another very, very important contribution. And indeed, it is a legacy that desperately needs to be carried forward, because in our society, we still have a huge deficit of scientific thinking. And it is really the responsibility of all of us, whether we are scientists or teachers or students of science or not scientists also. It is the responsibility of all of us to take this forward, because the scientific method is the best method we have to understand what is going on around us. It's not a perfect method, but it's the best we have, because it is self-correcting. This is the most important thing about the scientific method. This is just to illustrate what I said earlier, that we still have a very, very large science deficit in our society, especially in our country. This is the June 2020 eclipse, solar eclipse, where we saw a crescent sun where I am in Bangalore. And this is the historic Lal Bagh Rock, where we went to watch it. And it was we were a lonely bunch. I mean, this is all, there were maybe 5 other people, including these friends of mine, who, not including, but in addition to these friends of mine who are up there. And the rest of Bangalore city, which is a highly educated city with a lot of engineers and a lot of scientists and PhDs, everybody huddled at home. They kept their women and their pregnant women in, and they did not come out and watch the beautiful crescent sun. So I think it's really, really important that all of us carry this responsibility and propagate the scientific method in our everyday life, which Galileo started many hundred years ago. So in the Milky Way, I should show you this thing first. We now know from our study of the stars in the Milky Way and so on, that the Milky Way is actually in a spiral-like structure. So this is not a real picture, because we can never take a real picture of the Milky Way. We haven't gone outside the Milky Way, but this is a rendering of our understanding of what is the structure of the Milky Way. So the center of the Milky Way is near the constellation Sagittarius, the so-called teapot, and this circle represents the actual center of the Milky Way. And that is a zoomed in version. And the center of the Milky Way is about 26,000 light years away from us. So very interesting things are happening in the center of the Milky Way. But you will notice here, the circle is in a very dark patch of the Milky Way, which means that there's a lot of dust in the line of sight. And therefore, the real center, the heart of the Milky Way, is not accessible to us through visible light. So we need either infrared or radio frequencies in order to study what is going on there. Now, the team of Andrea Ghez, as an astrophysicist in the University of California, Los Angeles, used a very large telescope called the Keck telescope to study the stars in the center of the Milky Way. So this telescope is in Hawaii at an altitude of about over 4,000 meters. Now, there are 2 challenges in studying the stars in the center of the Milky Way. One challenge is what I already told you, that visible frequencies get obscured by the dust. And so we have to use either infrared or radio frequencies. Now, if you want to peer into the center and look at stars there, you need really very sharp images. And there is a limitation of the Earth's atmosphere that is illustrated here. So the light ray from a star should be a straight line that reaches right to our telescope. But because the atmosphere is there in between and there are density variations in the atmosphere, there are therefore refractive index variation, and therefore the light ray, instead of reaching the telescope directly, dances around. And so on the detector, instead of getting a single image, you get these multiple images of stars, but that happens so fast that what you actually see is just a blurred image. So Ghez used a technique of taking very, very short exposures of the center of the Milky Way so that she beats this dancing around due to the atmosphere. And she could do that by using the Keck telescope because it has an extremely large mirror of 10-meter diameter inside. So collects a lot of photons. So it's possible to take extremely short exposures in order to beat this dancing around. And it's actually not one big mirror. It is an array of these hexagonal shaped mirrors, which are all attached together. And there was another team in Europe, in Germany, the Max Planck Institute, led by Reinhard Genzel, and they were doing similar experiments using the European telescopes, which are located in the deserts of Chile. Now, they measured the movement of the stars, both Ghez and her team and Genzel and his team. But a few years later, they came up with an even better technique, which is to shoot out a laser beam into the sky and measure the density fluctuations, and therefore measure the refractive index changes, and then correct for them by distorting the telescope. So this is possible because their telescope is not one big mirror, but an array of these hexagon-shaped mirrors. So I've shown one hexagon in blue color just to show you that it's a hexagon, because it's not obvious that it's a hexagon, but you can see it on the edge that they are hexagons. So each of these hexagons, about that big, as you can see here in this picture. So this is one hexagon and here's a person. So each of these hexagons has controls behind it, which can be controlled in real time. So therefore, with this laser beam, you measure the distortions and then you distort the mirror using the controls behind each hexagonal segment in order to compensate for the refractive index change. So this is done in real time. So you can imagine it's very, very high tech. It's very, very sophisticated electronics and optics and everything. And because you can distort the image to compensate, you're then getting rid of most of the distortions that the atmosphere causes, and therefore you can get very, very sharp images. So that is illustrated here. This is the planet Uranus with its rings, and this image is without this technique applied. It's called adaptive optics, and it's without it applied. And on the right is with it applied, and you can see the enormous increase in the sharpness of the image. So Ghez and her team used this to study the stars in the center of the Milky Way. And here on the left is this bunch of stars. This is infrared frequencies. And you can see 1, 2, 3, 4, 5, 6, 7, etc. And then with the technique of adaptive optics of correcting for the atmosphere, you get what is here on the right. And what you see is much sharper images, much smaller. They look quote unquote smaller on these in this picture, but it's actually sharper because you can see that what looks like one star here is actually 2 stars, and so on. So you can clearly see the separation of stars, and this is a zoomed in version. So using this technique, Ghez and of course Genzel as well were able to measure the movement of stars in the center of our Milky Way. So those are the data I'm going to show you now, and it's in the form of an animation. So I'll explain first what I'm going to show you. So these are the kind of images that Ghez took. So this is a false color image. The multicolor splotches are stars. They represent the infrared emission from these stars. This star-like thing here is not a real star. It is just a star shape to mark that particular position. And you will see why that particular position has been marked. And up here in the top right corner is the date counter. So this particular image was taken in the middle of 1995. And they continue to take these images over time. And therefore, they were able to see how these stars shift, and therefore how they move, and therefore their speed. So I'll just show you this animation now. So you can see that these multicolored splotches are moving, and the dashed curves are just to guide your eye. They are obviously not real data, and you can see how the time is advancing. Now we are at 2008, 9, 10, and so on. It goes all the way up to 2019. So they've been observing these stars for a long time. In 1995, it was with just this big diameter telescope, and then later on with this technique of adaptive optics, which corrects for the atmosphere. Now, what you can see here is that, let me play that again. What you can see here is that the stars are moving. They're not moving in straight lines. They're not moving randomly. You can see very clearly that they are all moving in elliptical orbits. Moreover, the focus of all the elliptical orbits is the same thing, and it is that position marked by the white star-shaped object. So what does this mean? This means that these stars in the center of the Milky Way are moving in elliptical orbits, therefore they are Keplerian driven, just like our solar system. And therefore, if you know the speed, and if you know the sizes of these orbits, you can derive the mass of the thing that is driving these Keplerian orbits. It's a very straightforward classical physics calculation, and Ghez and her team concluded that there's got to be a black hole in the center of our Milky Way, which is 4 million times as heavy as our sun. The reason they were able to conclude that is that, you see, the nearest star which approaches that dark center approaches it pretty close, but then it emerges unscathed. Now, if there was something really big there, it would collide with it, and then its path would get deflected. Here we are seeing a star approach very close, but its path is not getting deflected. So this very, very large mass, which must be at the center, has got to be in a very small volume so that this star can move around it and then emerge without colliding and getting deflected, right? So therefore, they had a handle on the size also. And that relationship, remember, between the size and the mass, that tells us that the mass that they derive must be a black hole of 4 million times as heavy as the sun. In other words, 4 million solar masses. So this discovery, which happened in the late 90s, it won the Nobel Prize last year in 2020. This is an article, a very nice article that the director of the Keck Observatory wrote when the Nobel Prize was awarded. He was head of software at the time that Andrea Ghez was trying to do this experiment, and he says that at the time nobody thought that experiment would work. But Ghez persisted. In fact, she has made the statement, I grew up hearing the word no all the time. You're a girl, you can't do it. You're a girl, there's no way you'll get into MIT or Caltech, etc. So she was used to hearing no all the time, but yet plodding along. And she, of course, it is heartening that she eventually did make this fantastic discovery and win the Nobel Prize. So it is not surprising at all that her PhD thesis, which she submitted in Caltech in 1993, was dedicated to all the women scientists that she had known. So it is a duty and responsibility of all of us to correct the kind of barriers that Ghez faced and people face all over the world all the time. So you see, addressing the gender gap that does exist in physics, it's really not about encouraging girls and encouraging women, because the young girls and women are already interested. So they don't need to be encouraged. What does need to be done is to remove the barriers that they face. So being told by teachers, both men and women, that such and such pursuit is more suitable for women than men. For example, computer simulation work is better for women, rather than going out in the night to faraway observatories to do observations, or telling them that difficult things are not good for women. So the women should do science which involves easier techniques, or that women have to work really hard and in order to manage both their lives and their science and so on. You see, all these are the barriers. After all, caring for family or managing one's life is a responsibility of everybody, not just women. And so therefore, everybody has to work hard, not just scientists, everybody, whether it's scientists or football players or dancers, everybody, whether men or women, or everybody has to work hard in order to get good results out of whatever we are doing. So that is not something that only women need to do. So being told all the time that you need to work hard, you need to take things which are easier, these are the barriers that we really need to address. And all of us have this responsibility to reflect, whether we are scientists or teachers or students, all of us have a responsibility to reflect upon these things and to drop our biases so that we create a learning environment that is healthy for everybody. Okay, so there is a 4 million solar mass black hole in the center of the Milky Way. It turns out that every galaxy we have looked at, these are all real images of galaxies in the cosmos. It turns out that every galaxy we've looked at has such a giant black hole in its center. And not just that, when matter comes very close to this black hole, it will swirl around and eventually plunge in. And in the process of swirling around, it will be accelerated, heated to high temperatures, and therefore shine. That is what happened to Gargantua, the fictitious black hole in the movie Interstellar. And that was the idea of Salpeter and Zeldovich to explain quasars. And not only that, this swirling matter that plunges into the black hole becomes plasma because the temperatures are extremely high and there are magnetic fields generated. And these magnetic fields and plasma land up squirting out some of that plasma out into intergalactic space. This plasma also shines, particularly at radio frequencies. And so this is a superposition of and a false color picture in, a true color picture at in visible light and a false color picture in radio light. So you see in radio light this pink colored stuff and these two jets which are emerging and then diffusing out into intergalactic space. And in the middle is this galaxy, and these jets of plasma are originating in the center of the galaxy. And then there are other galaxies around and a couple of stars in the foreground and so on. So here is a simulation, a computer simulation using general relativity and magnitude hydrodynamics around a black hole to show how when matter swirls around a black hole, it could create these jets of plasma. So in other words, most of the matter will plunge into the black hole, but some of the matter will get squirted out. And the green curves represent the magnetic field lines. And then you can see the blue colored plasma emerging into jet-like structures and exiting out. So we know that this kind of a thing is possible. This is not real data. This is a computer simulation, but it shows that when you have a general relativistic object like a giant black hole and you have matter swirling into it, that matter would get converted into plasma, magnetic fields would be generated, and these kind of jets would emerge. And we actually see this in real images. So here is the earlier example I showed you. Here is another such example, again, a false color picture. And actually, this is an animation which, for some reason, is not playing, but we actually have images taken by this team from Boston University. And these are images taken at different times, just like the set of images of the galactic center. And then when you put all those images together to make an animation, you can actually see that these blobs of plasma are moving outwards. So this is another such example of a galaxy called Messier 87 in the Bhabha cluster. So here what you see, this is sort of a zoomed out version. And what you see is that the actual center of the galaxy is, so the galaxy looks like this. These are all the stars in the galaxy. And if you go to the very, very center, there are jets that emerge. And they emerge into intergalactic space extremely large, as you can see. And then form these very, very diffuse large plumes. Now, this was a galaxy whose center was also investigated, but not at infrared frequencies, but at millimeter wave frequencies, in order to really, really find the silhouette of a black hole. So the idea is like this. Now, suppose you have a spherical dark object, which is not a black hole, and you have matter swirling around it. You would expect this matter, let's say it's a very massive object, so you'd expect that this matter would be accelerated, heated to high temperatures, and shine. And so you would see this dark silhouette against that shining matter. But suppose this dark object is a black hole. Then what will happen? Einstein's theory says that this black hole is so massive that it will very significantly bend light. And so instead of having this dark object and lights, lit up matter swirling around it, where this part of the matter you would not see from here because the object is in the way. If this object is a black hole which curves space-time very heavily, then even the light from behind will curve over the black hole and we will see it. So we will see this sort of spherical structure of light around the black hole. And this was what was seen for Gargantua in Interstellar, which was a real computer simulation, correct computer simulation using the best physics that we know. And so this is the kind of shape we expect. And so this team of astrophysicists who are looking for such a silhouette, characteristic silhouette, looked at the center of this object called Messier 87. And they used not one telescope, but a whole array of telescopes. So these were all the telescopes they used. They all operated millimeter wave frequencies, and they were used as an array, which means that each of them is an interferometer. So basically, this is using the technique of interferometers. So some of you may remember your double slit experiments, where if you have two apertures, you obtain fringes in the interfered pattern, right? Now that can give you information about the actual source. So effectively, when you put such an interferometer together and try to image the sky, what you're effectively measuring is one Fourier component of the Fourier transform of the image of the sky. And so if you have several such interferometers, like you have here, so you have a whole bunch of them, so you have interferometers between every pen. And then if you use the rotation of the Earth, meaning if you observe an object for a long enough time, the Earth rotates in the meantime, and therefore the projected distance between the two elements of an interferometer changes with respect to the object you're observing in the sky. Then you measured more Fourier components. And then you invert the whole thing to reconstruct the image. So this was what was done by this team. It is called the Event Horizon Telescope. because they are trying to sample really the event horizon. And this is Katie Bowman, who led the software team, because as you can imagine, this whole measuring Fourier components and then putting them all together and doing the inverse Fourier transform in order to get the actual image is a very involved, computer intensive operation, which needs innovative algorithms. And they did this, and what they found was this. So this is the real image. This is the Gargantua simulation from the movie Interstellar. This is the real image. And as you can see, they what they got is exactly what was predicted, namely a silhouette of a black hole in the center of Messier 87. So this was a zooming in of about 1 million times. And that is the image. This was at radio frequencies, namely 230 gigahertz or 1.3 millimeter wavelength. And so now if I go back to what the Hubble Space Telescope did a few years ago, the Hubble Space Telescope looked at an area of sky in roughly in this region between Fornax and Ardennes. It looked at a piece of sky that was about 1/10 of the size of the moon. So all of you know that the moon, you know, what kind of size the moon occupies in the sky, the full moon, for example. But imagine 1/10 of a size of the full moon. That is the size of field that the Hubble Space Telescope looked at and stared at it, took an extremely long exposure, and this is what it got. 10,000 galaxies in an area of sky that was just 1/10 of the size of the moon. So every dot and smudge that you see here is a galaxy, except for these two cross-shaped things, which are foreground stars in our own Milky Way. Every dot and every smudge on this is a galaxy, which means that there are each of these 10,000 galaxies. There are 10,000 galaxies present in this small area, and each of them has about 100 billion stars. Each galaxy likely has a giant black hole in its center. And each of these stars likely have a planetary system. And each planet has the potential to harbor life. So I'll stop there. I'll take questions, of course.
Yes, thank you very much, ma'am. A wonderful talk has been given by you. It was a great treat for the astrophysicist. You have given a huge knowledge on how one can study a solar system by using the simplest way, that using Doppler-shaped law of gravitation. So that Einstein's theory, it was very nice, ma'am. Thank you very much. Now
Thank you, my pleasure.
I'll ask from the audience if somebody is having any questions from the audience. Yes, we will wait for 2 minutes. If somebody is having any question, can ask. Even I want to give something about, like there is a feedback link has been provided in the chat box. So every participant is requested to provide the feedback, because that will count your attendance, and as well as it will be helpful to provide you the certificate also. So I'll request all the participants to kindly just click on that chat box. There is a link provided for the feedback, and just provide us a feedback related to the webinar. Okay, so any questions to the audience? Yes? Ma'am, I think there is no question.
Yes, ma'am, I have a question.
Yeah, please.
It's Dinesh Kumar.
Yeah.
Ma'am, will you please tell us something about that Goldilocks zone?
Okay.
Like, how did we discover
yeah.
that Goldilocks zone is there in the Milky Way galaxy?
So Goldilocks zone was not really discovered as such that way. The Goldilocks zone is the zone in which we live. So the idea is that there is life on Earth, we know it. In fact, there is sentient life on Earth because we consider ourselves as, sentient beings. And so for life to emerge, understanding of what a life is like and so on, it is that, for example, water has to be in liquid form and all these sort of things. Which means that if life always originates on a planet, that is an assumption, right? I mean, there's, those of us who are science fiction buffs, we've read many science fiction stories where it is imagined that, sometimes life just originates in interstellar space or something. But suppose you assume that life has to originate on a planet, and if you make the other assumption that if life has to occur, it will be like the life we know. So it needs water in liquid form. Then this planet has to be in a certain zone where it's not too close to its sun that it is too hot, like Mercury, and it's not too far away that it's too cold, where water will freeze and won't be in liquid form. So there is this in-between zone. So obviously, what distance that zone is will depend on how bright the star is, right? So for a star which is much brighter than our sun, this zone will be much further than what the Earth is from our sun. Whereas for a star which is less luminous than our sun, then that zone will be much closer to that sun. So the Goldilocks zone is this zone which is sort of seen as the zone where water can occur in liquid form. And therefore, the assumption is that if water occurs in liquid form, then it is conducive to life. So is that understood? Is that so? People are constantly looking for. They also call it the habitable zone. So in this search, which I described for planets around other stars, there is a very strong bias towards looking for planets which are in this so-called habitable zone, or the Goldilocks zone, as you call it. So Goldilocks because it's neither too hot nor too cold, like how Goldilocks' porridge works. Just right.
Ma'am, it's Vibhor Kavade.
Yeah.
Ma'am, I want to ask you about white holes. What do you think about white holes?
Yeah, so I'm not the right person to answer that. I mean, these are speculative objects, and there's no, evidence for them so far. So they're theoretical constructs, and I'm not the expert on that. So you should ask someone else.
Ma'am, there is good and there is bad also. Then
Sorry?
why not white?
Yeah.
Ma'am,
Sorry?
good, there is bad also exist. Then why not white holes?
No, I didn't understand. You said there is good and bad. Sorry.
Yes, ma'am. When there is exist a good, then there also exists a bad thing, like a black holes. Then there are also good. I mean, white holes also.
No, I don't agree with that analogy at all. I don't think black holes are good or bad. They're just facts, and it's part of nature. So we don't we apply the word good or bad, to our lives, right? So yeah, I don't think it's appropriate to say. So that is not an argument. The argument is, can you show something exists on formal grounds, that is using mathematics that is self-consistent, and then can you make predictions, and then can you test those predictions using experiment observation, right? So I don't know the status of where the white holes stand on formal grounds, but there is no evidence for them so far.
Thank you, ma'am.
Hello, ma'am.
Hello.
I'm Shastri.
Go ahead.
Yes,
Yes.
ma'am. I've heard that black holes have intense gravitational pull and nothing can escape them. But I've also read from some sources that they emit some kind of thing. I mean, I've heard that from Stephen Hawking that it emits some kind of thing. Can you explain more about that? I mean, I'm not clear in that concept.
Right. So, yeah, black holes by themselves are not expected to emit any radiation by definition, right? Because that's how we define it. Now, we are able to see evidence for them because the matter that comes, any matter that comes close to a black hole will be attracted by the black hole, will swirl around it, get heated, eventually will plunge in. Most of it will plunge in. But in the process, it will get heated and shine with such huge luminosities that cannot be explained by anything else. So we know that they are black holes. Now, as I said, 100% of the matter doesn't plunge in. Some of it comes out as plasma, but that is not coming out of the black hole. This is just that the matter which is swirling around, all of it doesn't plunge in, some of it comes out. So this is not matter coming out of the black hole. Hawking radiation is something else. So Hawking applied quantum physical ideas to what was happening around the black hole, and he predicted that black holes would show Hawking radiation. Now, this does contradict what I said earlier, which is that nothing comes out of a black hole. And so it is a predicted effect that contradicts that, but it is at the level of theory, and there has been no evidence for it so far. Now, it also predicts that small black holes will show more Hawking radiation. And all the black holes we know are large black holes. So the smallest black hole we know are a few solar mass black holes. So the Hawking radiation from them is extremely low, and also predicted radiation from them is extremely low, and in reality they have not been seen. On the other hand, there has been speculation about small black holes, electron-sized black holes, but in the laboratory we've never seen a black hole. The only black holes we have evidence for are large and in the cosmos. Yes, so Hawking radiation, in the short answer to your question, is yes, Hawking radiation is predicted by applying quantum physical ideas to a black hole, but so far none has been seen.
Okay, ma'am. Thank you.
Good morning, ma'am. This is Shweta Dhage.
Yeah, go ahead.
Okay, so ma'am, I've been very curious about Olbers paradox for a quite long time, and all I got from sources was that mostly it is because our universe was expanding. So is it the only solution for Olbers paradox?
Yeah, I mean, Olbers paradox actually, it deserves a whole new a talk by itself. It's a very interesting.
Yes, ma'am.
Yeah. But yeah, that is, the idea of the paradox was that if everything is just the way it is now, we see, zillions of stars in the Milky Way, and we see zillions of galaxies and so on. And so the idea is that just one second. I forgot to, because of all that trouble in the beginning, I put my phone on silent. Sorry about that. Yeah, so if everything is just the way it is now, like a static situation, then every line of sight should touch a star. So the whole sky should just be very bright, right? But the point is, what I think I illustrated to you, that we are always out of date, right? So what we are seeing, the further something is, we are seeing it from an earlier time.
Yes.
So from the moon, it is 1 second earlier. From the sun, it is 8 minutes earlier. From the next star, it is 4.5 years earlier from the nearest star. From most of the stars in the Milky Way, it's many thousands of years earlier. And then when you go to galaxies, it becomes millions of years earlier, billions of years earlier. So then you're starting to, when you're looking at further and further things, you're starting to reach the big, earlier times in the universe close to the birth of the universe. So you will reach a time when there were no stars at all.
Yes, ma'am.
Yes, now I
Okay,
think,
ma'am, I had another question
Yeah.
regarding Women Scientists Association. So can I go ahead or can I contact someone else?
If it's about the organization, then you should talk to somebody. I'm not from that organization. Yeah, so you should talk to somebody. I think there are people there from there here in the audience. I'm not sure. But
Yes, ma'am. Thank you very much. It was a wonderful session.
thank you.
yes, I think now most of the questions completed, and ma'am has given a great knowledge. Yes, and if there is any
I think
question,
Manasvi Shetty wants to say something.
Yes.
Namasvi, this may be the last question. Namasvi, go ahead, Namasvi.
Okay, ma'am. I'm sorry for the delay. I have to ask one question.
Yeah.
I am not exactly clear what is the difference between a quasar and a normal star.
Oh, okay. Yeah, maybe I didn't make that 100% clear. So, quasars mean the expansion of quasars is quasi-stellar radio source. So, quasi-stellar means almost like a star. So, it got that name because it also looked like a regular pinpoint of light, just like any other star, right? But it was obviously not a star because it didn't show the absorption lines of the spectrum, and it shows the emission lines instead. Now we know that it is the nucleus of a galaxy like the Milky Way. So if you there are all these galaxies. They have a giant black hole in their center. There is swirling matter in all galaxies. It may not happen, but in some of the galaxies, some swirling matter has reached in the very close vicinity of this black hole, and therefore swirling around it, heated, shining very powerfully. So we see that. Now, if this galaxy is close enough, we will see that, and we will see the light from all the stars. But as we look at more and more distant galaxies, if the giant black hole in the center is doing this thing about swirling matter and heating it up, then the luminosity from that central part will be so high that it will blind, it will overwhelm all the light from the stars. And so we will see it as a pinpoint of light. Whereas if that same object, you bring it very, very close to us. So the example that I gave, 3C273, although it looked like a pinpoint of light those days, now with better telescopes, we've actually imaged the stars around this thing and which are in the galaxy. So to answer your question in short, a star is a single object which shines due to nuclear fusion. A quasar is an accreting, we call it. Accreting means this matter swirling into it. A quasar is an accreting supermassive, meaning giant, meaning more than 1 million solar mass black hole at the center of a galaxy. So the quasar is sitting in a galaxy with 100 billion stars, whereas a star is a single object.
Okay, ma'am. Thank you.
Is that clear, or did you have any more questions?
No, ma'am. That's it.
Okay.
Yeah, thank you, ma'am. The topic is so big that one cannot cover it even in an hour.
Yeah.
It requires more time, I can understand. But it was very nice, wonderful talk, ma'am. So now I'll request Dr. Sonone, sir, to kindly give the vote of thanks, sir.
Yes, madam. Thank you, madam.
Yeah.
Respected our most distinguished chief guest of the day, Dr. Devaki Ramanathan, madam, retired senior scientist, BRNS-DAE, Mumbai. Respected Jairam Khobragade, sir, Director, Institute of Science, Mumbai. Distinguished speaker, Professor Prajval Shastri, madam, retired professor from Indian Institute of Astrophysics, Bangalore. Our HOD, Professor Ajay Chaudhary, sir, dear professors, colleagues, and friends. It is my privilege to have been asked to propose the vote of thanks to all who have helped us in making this seminar such a grand success. First of all, I would like to thank to our chief guest, Dr. Devaki Ramanathan, madam, for guesting and presiding the inauguration of the webinar.
Buy something which is acceptable to you.
Thank you very much, madam, for your valuable guidance. I would like to thank our distinguished speaker, Professor Prajval Shastri Madam for excellent presentation and making this webinar interesting and
But this one,
meaningful.
when they come, let them see that what is to be done.
I would like to thank to our director Jairam Khobragade sir for sparing his valuable time with us. I would like to thank for our beloved Professor Ajay Chaudhary sir, Dr. Kulkarni sir for their moral supports and guidance. I would like to thank to the coordinator of the webinar, for making this webinar a great success. I am happy to express vote of thanks to our staff members who have made this seminar successful. We are also grateful to all sponsoring organizations like BRNS Mumbai and Indian Women Scientists Association Mumbai. Finally, I would like to thank to the wonderful participants who have turned up in such a great numbers from different departments, institutes, colleges. Once again, thank you all of you for your cordial cooperation. Thank you very much.
It was meant to be for the.
Yes, thank you very much for the presentation. Just again, one more time, giving remembrance to everyone that you have to fill up the feedback. Those who have not filled up the feedback, they can just click on the chat box. The link is provided in the chat box.
What will you do? Even if you put it down,
that the webinar has been completed, has accomplished. So
Thank you, madam.
Thank you.
Direction from one side.
Thank you. Prajval Shastri madam.
Okay,
And
thank you.
Nathan madam. Thank you very much.
A wonderful talk, ma'am. Very nice. Thank you, everyone.
Yeah, thank you.
Thank you, madam.
Thank you.